Start. Hello everyone, welcome to the seminar Computer Architecture class again. So I'm Geraldo, and today I'm going to talk about, I'm going to give an example talk about our SimDRAM paper, which was presented in ASPLOS. More than you understanding.
The web stream is not working. Is it incorrect?
No, I mean, like, I'm seeing something here.
Yeah. Oh, yeah.
Is everything okay?
Yeah.
Okay, great. So instead of you learning about SimDRAM, of course, important, but I want to also highlight some important things. Maybe it's because of the camera, but it's okay.
Can you move the slide so I see at least a slide move or not?
See.
At the same. Just give it a second. It delays though. The slide is not moving.
Can we start the live stream again?
Did you share yours?
Okay, now it moves. Okay.
Okay, just there is a huge delay.
Okay, I understand.
Okay. So hopefully everything goes well. So instead of you focusing on learning about SimDRAM, I want you more to pay attention about the structure of this presentation. And after the main part of the presentation, I'm going to discuss some tips for your presentation during this seminar class, some things for you what to do, and some things for you to not do during the presentation. So before I go into details on SimDRAM, I'm going to give a brief summary of what this work is about. So the motivation of this work, and my pointer stop working again, is that processing use. I gave a talk some time ago on memory-centric computing, so probably already familiar with this concept. But that is this idea of using memory cells to perform computation instead of using them only to store data. And prior works have shown that we can use those memory cells to perform book-bitwise operations and accelerate some applications. However, the applicability of such systems are quite limited to support only few operations. So in that case, Boolean and or not operation or no copy operations. Also, there was a lack of flexibility to implement new and arbitrary operations. And also, it might require significant changes to the DRAM subarray organization in case you want to implement something more complex, for example, as an addition operation. So the goal of this work is to mitigate those three problems and design a process using DRAM framework that can first extend the implementation of process using DRAM operations to other operations like addition or multiplication, provide a flexible way for the user to implement arbitrary operations as needed inside DRAM using the available process using DRAM primitives, and also at the same time minimally change the subarray organization or subarray design. So to do so, we propose SimDRAM, which is a three-step framework, if my pointer works, which is an end-to-end process using DRAM frameworks, which is going to provide the programming interface, the instruction set architecture, and the hardware support to enable the efficient implementation of complex operations using process using memory primitives, while providing the user the ability to implement arbitrary operations as needed. At the same time, it's going to transform the DRAM subarray into a massive parallel SIMD execution feature. So we extensively evaluate SimDRAM, and we observe that SimDRAM can significantly improve throughput and energy efficiency compared to a baseline CPU, GPU for 16 different in-DRAM operations. While we can provide 21 times and 2.1 times the performance of a GPU and a GPU for seven real-world applications. So this is the outline for this talk. So first I'm going to briefly talk about process using DRAM architectures, and then I'm going to give a brief background on DRAM operations and process using DRAM operations. Then I'm going to introduce of SimDRAM framework, talk about our system integration, briefly talk about our evaluation, and finally conclude. So starting with processing using DRAM. So as probably you already know at this point, data movement is a problem or in a major bottleneck in current systems because you need to move data from a power-hungry and narrow channel every time that you want to compute something on your computing engine. So prior works have shown that in mobile systems, actually the energy consumed for data movement for several applications is account for around 70%, 60% of the total system energy. To mitigate this problem, there is this paradigm called processing in memory, where we are going to move computation near where the data resides. And there are two flavors of processing memory, processing using memory and processing near memory. So regardless, both flavors reduces or eliminates the data movement bottleneck because now you don't need to communicate through this narrow memory channel. And so in particular, processing using memory is what we're going to talk in this book over here. So in processing using memory, we are going to use the analog properties of the memory cells themselves to perform computation. And this allows us to leverage the massive internal parallelism available inside memory devices themselves. I think they're so slow. So,
okay, so that you're
yeah. Sorry. Okay. So, also there. So prior works have shown that we can leverage this idea of using the analog properties of the memory cells to perform different operations, like simple logic operations like AND, OR, or XOR, or some prior works propose ways of doing some few complex operations like addition or multiplications. So, maybe I should move this here. So before explaining how processing, so those things are achieved, how those operations are achieved, I need to give a brief overview of how a DRAM model is organized. So a DRAM model constitutes of multiple DRAM chips. A DRAM chip has several DRAM banks. A DRAM bank has several DRAM subarrays, which is a 2D array of DRAM cells, where we have horizontal lines connecting DRAM cells through a load line, and vertical lines connecting DRAM columns through a bit line. So the bit lines are connected to a group of sense amplifiers, which is called as a collective as a low buffer. A DRAM cell itself constitutes of an excess transistor and a storage capacitor. Okay, in order to access data from a DRAM model, the memory controller issues three main operations. Activate, a read, or a charge command. So to read that data, to read this voltage level stored in the storage cell capacitor here, first the memory controller is going to send activate command. This activate command is going to first assert the word line and connects the it's going to raise the word line, connecting the storage capacitor to the bit line. This is going to allow the capacitor to lose charge to the bit line, generating a perturbation. The sense amplifier is enabled. It is then going to sense this perturbation voltage level and amplifies that perturbation level to a CMOS readable value, so either 1 VDD or 0 ground. And then the data is going to be restored back to the storage capacitor to its full state. So after that, the data is latched to the sense amplifier, and the memory controller can send read and write commands to the latched data over there. In the end, when there is no more data to be read from that particular sense amplifier, the memory controller issue a pre-charge command, which basically disconnects the word line, which connects the storage capacitor to the bit line in this storage capacitor, and then pre-charge the bit line to the original reference voltage, usually half VDD for the next access. So prior work, and finally disable the simplifier. So prior works have shown that we can implement or we can leverage these operation principles of DRAM to implement in-DRAM row copy or majority operations. So let's say that you want to copy a source row A into a destination row B, where both source rows shares the same bit line. So Ambit proposed this sequence of DRAM commands called activated precharge, which allows us to copy source row A to destination row B without the intervention of the CPU. So in the first activate, is going to operate exactly as I mentioned before. The word line is going to connect the storage cell capacitor to the bit line. This amplifier amplifies the voltage level from the source cell capacitor and latch the data. The second activate is going to allow connecting the destination row, enhanced cell in the destination row to the bit line. And since the sense amplifier has a higher pool than the capacitance in the bit line or the capacitance in the storage capacitor, the data that is latched there is going to be written to the destination row. Likewise, we can also implement majority operations of 3 rows, A, B, and C, that share the same bit line inside the DRAM subarray by issuing this sequence of command that is called triple row activation. So this command activates simultaneously 3 DRAM rows at the same time, which allow the 3 DRAM cells to share is charged to the bit line voltage enhanced to the simplifier at the same time. So the simplifier is going to then pull the voltage level from the bit line to the majority of the voltage levels of the cells stored in A, B, and C. And if the majority of in this example here, the majority of the cells is equals to VDD, if at least 2 of the storage capacitor has VDD voltage levels, they are going to be amplified to VDD, otherwise it's going to be amplified to 0. And finally, the data is overwritten to the 3 DRAM cells at the same time. So by controlling one of the DRAM rows, we can implement either a OR operation or an AND operation. So if you set one of the input of a majority to 0, this is equivalent to doing AND of A and B. And if you set one of the majority inputs to 1, this is equivalent to doing OR of A and B. So Ambit proposed some simple modifications to the DRAM array organization to allow us to efficiently implement these triple row activations. Namely, they are going to have this 16 dedicated rows connected and 2 pre-initialized rows, which holds all 0 values or all 0 values to control the AND or OR operation, and then the regular data rows that holds the data from the user. So the data, the rows in the bitwise rows share a special row decoder, which with a single row address allows you to activate 3 DRAM rows at the same time. So all of these modifications incurs less than 1% of area overhead on top of existing DRAM chips. So to summarize, other prior works or other memory technologies are also similar like in DRAM, and then hence they can implement processing using memory operations like flash or non-volatile memory devices. However, all of them share some shortcomings. So the first one is that they can only implement some simple operations. So here we have the example of AND and OR operations. And this limits its applicability to a large set of applications. And also it lacks the flexibility to support any other arbitrary operation. So if you want to do, for example, a multiplication or a division, there is no protocol to do so in DRAM. If you want to do that, there was some few prior works that proposed to do some changes inside the DRAM array, so you can implement some few operations like addition, but those changes are quite costly. So because of that, we need a framework that can efficiently implement complex operations using those cross-using memory primitives that I showed before, the majority operation and the row copy operation, while providing the user some mechanism to implement new operations as desired. Therefore, our goal in this work is to design such a framework that can efficiently implement complex operations in DRAM and gives the user the flexibility to support new desired operations while minimally change the DRAM array architecture. And to this end, I get to SimDRAM. So the key idea of SimDRAM is to provide an end-to-end framework that gives support for cross-using memory operations. So basically, SimDRAM is going to aim for those three goals that I mentioned before. So efficiently implement complex operations in DRAM, allow the implementation of complex arbitrary operations as required, and at the same time transform the DRAM array into a massive SIMD substrate while minimally modify the DRAM array organization. So to do that, SimDRAM leverages two existing key ideas. The first one is the use of vertical data layout for operands, for bitwise operations. So what this allows you to do is allow us to have an efficient way of sharing data across different operands stored in the same column at the same time. So the problem of doing something like addition inside the DRAM array itself is that there is no if you have a element, imagine that everything is transposed in the other array. So the yellow is in this row, the green in the other row, so on and so forth. And if you have to propagate a query from one column to another, you don't have a way to do so because there is no connection between this column here and this other column here and the other column here. So what we do is that instead of organizing data horizontally, we are going to organize data vertically. By doing so, if I'm adding this element and this element here together, and this produces the query for the next addition, for example, for this element, they are all sharing the same column because they are vertical aligned. So this allows us to do implicit shifting operations. So if you want to shift this bit to this bit, I just need to do a row copy from here to there. And at the same time, it enables massive parallelism because now you can imagine that every single column inside the DRAM array is going to operate as a SIMD lane of a SIMD processor. And over here, we only have 4 of them, but in current DRX organizations, we have around 65,000 of those columns. So it's extremely massive, very massive parallel engine. At the same time, we are going to fully use majority operations. So prior work was always using Boolean operations. So they were setting one of the inputs of the majority to either 0 or 1, and using that for doing computation. Here we are going to use majority-based algebra, and we are going to fully leverage its capabilities. So compared to using only AND, OR, and NOT operations, we can have higher performance because we can have lower amounts of tuple row activations being issued to DRAM, and also higher throughput because the latency is lower. Of course, lower energy consumption as well. So based on these two key ideas, we propose this 3-step SimDRAM framework. So the first step, the framework takes as input a desired operation that the user wants to implement, described in terms of AND, OR, and NOT logic. So the first step is going to convert that representation into a majority NOT based representation of that same logic. The second step is going to map the generated majority NOT circuit into sequence of in-DRAM operations, so either row copy operations or tuple row activations. And this is called a microprogram. In the end, the microprogram is storing in memory for future use and added to the CPU ISA so that the programmer can instantiate this new operation in DRAM. So during runtime, the user enables SimDRAM by using these new ISA instructions explicitly in the code. And then we design a control unit inside the memory controller of the processor that is going to read and fetch the microprogram for this particular operation and dispatch the sequence of DRAM commands in the microprogram to the DRAM model itself, so you can perform the computation efficiently. So let me see how I'm in time because I feel a little bit that I'm slow. So I'm going to try to go a little bit faster in the details because the goal here is not to get too much into the details of this mechanism. So the first step of SimDRAM is going to convert the majority, the in or not representation of the input sequence to a majority-based representation of the same circuit. So as I said before, we can easily convert a graph that uses, or a circuit that uses and or to a graph that uses majority gates because of this equivalence. So as I was saying before, if you set one of the inputs to 0, 1, you have this equivalence to and or node. So if you have this circuit over here, that's the circuit of the carry out for a RIP carry header. Converting this to a majority based graph is simply following this equivalence and change the gates. So it's quite easy. However, this leads to a not efficient circuit because, as I'm going to show next, if you apply optimization or minimization algebra to minimize the number of majority gates here, you can reduce the number of transistors or the number of majority cells that are here to actually only one majority gate. So the first step is actually going to do that. We implement this grid optimization algorithm that, again, if you think about Boolean minimization, if you think about the Morgan's law, all those things apply to majority gates. So we apply this optimization to the circuit, and then we have, an efficient implementation of that initial and or not based circuit using only majority gates. So this is going to translate later on to fewer a number of triple activations that you need to execute. So the first step is going to generate the sequence of in-DRAM operations that can implement that majority not base graph that I showed before using row copies or triple row activations. And we call the sequence a microprogramming. So there are two steps or two tasks involved over here. The first one is to allocate DRAM row to operand, and the second one is to generate the microprogram themselves. So starting with the first one, we have my computer is going to be slow now. Okay, great, didn't crash. So the problem that we have over here is that if you recall from the subarray organization that I mentioned before, we only have really few DRAM rows that are connected to this special bitwise decoder that can activate 2 DRAM rows at the same time. So when you have a graph with many inputs, we need to find a way, or many edges, we need to respect this constraint over here. The second constraint that we have when we are mapping inputs of the graph to the subarray organization is that when you do a triple activation, that operation is destructive. So if so slow. So if you do a triple activation, the data of all the inputs is rewritten to the output value of the triple activation. Sorry for this glitch. So basically, this allocation algorithm is going to take these two constraints into consideration by going through every single edge of this majority graph and mapping those edges to those rows, those 16 DRAM rows in the bitwise group in a grid way. So we'll map one by one. And then, so first we'll assign as many inputs as 3 rows that we have over there. And once you don't have 3 inputs, we try to reuse the inputs from the previous triple activations or for the follow-up triple activation that have data dependence over there. So we can reuse. So the second step, so once you figure out which rows which edges goes to which DRAM columns, basically you can go through the edges and then start generating sequence of row copy operations and triple row activations to execute this operation inside the DRAM array itself. We implement 2 optimizations on top of this initial sequence of DRAM operations. The first one is going to coalesce some row copies and some majority operations because of the principles of that special row decoder that I mentioned before. I'm not going to enter in details over here. And the other step, and the second step is going to generalize, because before we are doing this computation only for 1 bit over here, so it's going to generalize this computation to n bits. So in the end, if we have a 32-bit addition, the sequence of operations is going to repeat 32 times because it's a bit serial execution mode. So the final microprogram is stored in a reserved DRAM space for future use, and new ISA instruction called BBOP is added to the CPU ISA so that the programmer can interface with that program. So the third step, we modify the memory controller inside the CPU processor to handle the execution and dispatch the triple row activations and row copy operations to DRAM as required by a given operation that the user instantiates. So you're going to load these microprograms and then issue one by one to DRAM. So in the end, we have the execution of the triple row activation inside the DRAM array itself. So to make all of this to work, we need to consider several system integration challenges. The first one, and the one that I'm going to discuss here, is, as I mentioned before, the data in SimDRAM is transposed to this vertical data layout, right? But your CPU still uses data in a regular horizontal data layout. So you need the efficient accelerator or efficient mechanism that can convert data back and forth from one layout to the other. So to do that, we implement this data transposition unit between the last level cache and the memory controller, which is going to identify memory objects which are going to be used by cross-using DRAM operations, and transparency from the user transpose the data on cache line evictions from the horizontal to vertical data layout and to the vertical to the horizontal data layout on a read from DRAM. So we evaluate. I'm going to briefly talk about the evaluation. So we evaluate SimDRAM using a simulator, the Gen 5 simulator, and we compare it with a baseline CPU, a GPU, prior processing DRAM system called Mbed, and we evaluate several configurations of SimDRAM for a DDR4 device using 1, 4, and 16 DRAM banks. We implement 16 different in-DRAM operations using this three-step framework, and we use these operations to accelerate 7 real-world applications. So starting with the throughput analysis over here. So in the x-axis we have the baseline system, CPU, GPU, and Mbed, and the y-axis we have the average normalized throughput in log scales in throughput per second for SimDRAM with 1 bank, 4 banks, and 16 banks. So compared to the CPU, SimDRAM 1 bank provides SimDRAM provides 5.5, 22, and 88 times the throughput of the CPU. It does not provide much throughput compared to this GPU for 1 bank, but with 4 banks we already provide 1.5 times the throughput of the GPU, and with 16 banks we can provide 5.8 times the throughput of the GPU. And we see similar trend for Mbed. So in conclusion, SimDRAM significantly outperform all 3 state-of-the-art systems for the wide range of operations. So here we have energy. So we have energy efficiency in performance per watt for the CPU, GPU, and Mbed for those 16 operations. And again, SimDRAM significantly improve energy efficiency compared to the CPU, GPU, and Mbed. So we conclude that SimDRAM is a more energy efficient substrate compared to all of the evaluated systems. Compared to the 7 real-world applications, in the y-axis here we have the average speed up across those 7 applications, and we see that SimDRAM significantly outperforms the CPU, outperforms the GPU when using 16 DRAM banks, and significantly outperforms Mbed. So in conclusion, SimDRAM is efficiently and effectively accelerates several commonly used real-world applications. So we have much more analysis in the paper, and I invite you to check our paper for discussion over there. So in conclusion, in this work, we implement SimDRAM, which is this end-to-end framework that provides the the programming interface, the ISA and the hardware support to implement complex operations inside the DRAM array itself, while allowing the user the ability to implement arbitrary operations as needed, and transforming the DRAM array into a massive parallel in-DRAM substrate. So we extensively evaluate SimDRAM, and we see that it significantly outperforms CPU, GPU, and a prior processing using a DRAM system for 16 DRAM operations and several real-world applications. So we conclude that SimDRAM is a promising processing using memory framework, which can ease the adoption of processing using DRAM architectures while improving performance and energy efficiency. So this was the conclusion of the talk. Hopefully I didn't bore you so much. I don't know if there's any question about SimDRAM themselves. Otherwise I'm going to enter to the analysis.
So in the ISA, the BBO operation, what information is in one such instruction?
They input. So there are 3 types of them. So I'm going to talk about the common one for arithmetic operations. It's basically the address of if you have addition, for example, the address of these 2 input arrays and the initial address of the output array, the bit precision of that computation, for example, because it's bits like if you want to do a 32-bit addition or a 16-bit addition, and also the size of the arrays. If it's like, I don't know, 64 gigabytes or something, megabytes or something like that. So it's basically that information that's encapsulated that over there. And each BBO has a equivalent opcode, and basically it works similar to like a simple in-order core type of system work. So we use that opcode to address a table, and from this table gets the microprogram.
Mm-hmm. And so one more thing, the microprograms for these instructions are not like optimized and computed dynamically. Those are
one-time effort. So you generate them once, and then you store them in memory. And then when you are dynamically using them, you just keep generating them. You just fetch them back and forth from that table that I mentioned before.
You generate them once, like during the execution of the program?
Once in life. Once you generate them, it's just a sequence of operations that keeps. The only thing that needs to change is the input arrays once that is generated. Thank you. So, okay, so I'm going to try to go quickly on the analysis. So some important notes for when you are doing your own analysis over here. It's really important for you to sort the items that you are presenting for more important item to less important item. And what do I mean by most important item? So how you judge idea, right? Usually, the best thing that can come from idea is novelty, right? So you discover something that no one discovered before. So that would be the top priority. And then it goes lower and lower priority. For example, you can have a really good idea and a really bad implementation. So, for example, what is the name of the brothers that invented the airplane in the US? So they had a really good idea for inventing the airplane, right? But that particular design was not so efficient. Like it did what it was do, but it's not that design that we use for commercial aircraft right nowadays, right? So you can have a good idea with a bad implementation, but it still is a good idea. Or you can have a good idea with a bad evaluation, which is also, but regardless, the idea is still good. You just need to do more work to comprehensively evaluate that idea. The less important thing is presentation. So presentation is really important when you're communicating as a scientist, because it's how people are going to perceive our work. You can, if there is still some really good idea in a bad presented paper or in a bad presented work, you can claim that, okay, maybe it's like a language barrier or some other barrier over there, but that barrier shouldn't block the idea to come out to the world, because in the end, what we care about are ideas and how great or how important, how much impact that idea can have. We can always improve evaluation, we can always improve presentation, we can always improve design. But generating in the initial idea is really critical. So try to sort that list in that particular order from the novelty down to the presentation. So I put here some strengths. So this is my paper. So of course I'm biased. So this is the first work that provided concrete methodology to generate arbitrary process memory operations. So this extends the applicability of cross-use memory systems. So this is related to the idea and the novelty of the idea, right? The second item that there explores a new execution model for cross-using DRAM computation. This is more related to implementation, right? So by implementing that idea, I can enable something. And this enabling here is this case here, is this very wide SIM engine inside the DRAM array itself. The evaluation is extensive. It didn't present it, but the paper is quite. There is a bunch of things in the evaluation, including other cross-using DRAM or cross-using memory architecture. So it's a good thing to have. And finally, the paper is well written, and there are a lot of details regarding its implementation. So as you can see, I went from the novelty of the idea down to how the idea is presented in this list over here. Of course, you can agree or disagree. The topics is not that important. It's just more for you to understand the format. Weakness. So if you look at the SimDRAM paper itself, there is a session, and this is quite common in many papers. And the session is called SimDRAM limitations. So you can go to the paper and try to find the section and just copy and paste the limitations that the author provides. So float point operations. So SimDRAM does not support float point operations, or operations that require shuffling data across different bit lines, or synchronizations. So you can come here and just write down those, but this is a bit boring and expected because the authors already identified those limitations themselves. So it will be good if you can think a little bit outside the box. So how do you think outside the box? You need to reflect about the paper that you read. So again, those are ordered by novelty to presentation. So the first thing here is actually related to the idea. So when you are doing computation in a bit serial way, now the latency of your computation depends on the bit precision that you're going to execute. So if you have, meaning that if you have a 32-bit addition, that is going to take linear twice more to execute than a 64-bit addition, and so on and so forth. If you have a multiplication, that's much worse, because multiplication in bit serial algorithms is scaled quadratically. So if you have 32-bit multiplication, that's going to be 4 times 64-bit multiplication is 4 times lower than a 32-bit one. Besides that, there are other things that encourage latency that's not trivial. For example, data transposition that I mentioned before, right? Even though we have accelerators to do that, still you need to move data back and forth from one format to the other. So those are limitations of the idea itself, right? Like you can probably, if you think a little bit more, you can design a better system that can mitigate those two problems over here. Second one is that maybe you are not so familiar with this, but if you know a little bit about the literature of processor design over the years, or you took design, the design in computer architecture class that we give here, you know that this is not the first time that someone has proposed to use very wide SIMD engines to compute as a accelerator or as a processor, and that failed in the past. And it failed in the past because it's really hard actually to exploit a lot of data parallelism from the application at once. It's really hard to extract that data parallelism. It's really hard to identify the data parallelism. And often what we see is that applications actually have varying degrees of parallelism. So yeah, you are enabling this, but the question is how useful this is questionable. Third, programming this engine is done manually, which can be quite complicated. So as I showed before, we have these big block operations, right? And the user needs to rewrite the codes to include those big block operations. And this can be quite handy. If you ever program in assembly, you probably know how daunting this is. And the last thing, again, related to presentation, evaluation is done only in simulation. It then is unclear if the ideas can be ported to commercial off-the-shelf DRAM chips. As you're going to see next, this is possible because Mario is going to talk about it. But again, the important thing is that I went from questioning the idea. I didn't question the novelty because the paper is published, so probably there is some novelty there. But I start questioning the ideas of the paper, and then I went down to presentation and evaluation, because we can always improve presentation and you can always complain about the evaluation. So the takeaways is what you take away from this paper. So I take away that now you can implement processing DRAM for key arithmetic operations at high throughput and high energy efficiency. And you can implement arbitrary process memory operations by orchestrating those process memory primitives. And then the most important thing, other than the presentation, is the discussion point that you come up with. So the first tip that I have for you is to build upon the weakness that you just identified before. There is probably something there. The second tip is to be concrete. So Girai talked about a little bit about this. So if you come here with like a discussion point that is too open, it's really hard for people to grasp on that discussion point and try to brainstorm with you. So try to do that initial brainstorming with yourself or with your mentors, and from there we can develop something and then discuss that idea in a more concrete way. So here I have an example. So I put that example there. For example, that bit serial execution mode incurs non-trivial costs, right? So how can you, for example, if you think about, okay, I want to get rid of this data transposition unit. So what are the changes required to DRAM to do this process using DRAM operations and at the same time operate on horizontal layout data? So we need to basically, as I mentioned before, find a way to shift data across different DRAM columns, right? This is why we are transposing the data. So there are many options. The first option is to directly interconnect the DRAM columns with some sort of interconnect, but this has some cost. So you can think about this cost. Is it high cost, it's low cost? Or you can think about alternative arithmetic operations. So maybe you don't need to use bit serial. Maybe you can use bit parallel additions like what is the thing? CSA or some Congestone adder, some other thing. But what are the challenges of implementing such algorithms, for example, using this substrate? So I didn't further develop those because those are actually follow-up books, but that we are working on. But ideally, we would actually answer what's the cost and what's the challenge, and then come here and present them, and people can question you in a more concrete basis. So the other example here is this very wide SIM engine has failed in the past. So how can we mitigate underutilization that potentially can happen because of this very wide SIM engine that you're implementing? So for example, from a hardware point of view, you can chunk the DRAM array to operate in smaller segments of the DRAM row itself, right? So we are operating at 65,000 rows because when you issue activation, all of those all of the cells in our road lines are connected together, right? But you can chop that off and make it smaller subarrays. And then in the end, you're going to end up with smaller SimG engines, right? With smaller granularities. Maybe more SimG engines, each one of them with smaller granularity. And what's the cost of doing that? Is there a easy way of doing that, or is it always hard? From a software point of view, can you exploit other type of data parallelism? For example, if you have other applications running in the system, maybe you can make portions of a DRAM subarray for one application and portions of another DRAM subarray for another application, and collocate them together so that you can improve utilization. So all of those things are ideas that you can develop and build upon and discuss if they are good ideas or bad ideas. But if I just come here and tell you, ask you the highlighted part here in green, in bold, it's hard to discuss, right? Because there are so many alternatives ways of doing things, then it's just hard to come up with the ideas at first. So is there any question related to those? So if not, I'm going to give you some discussion, some tips on preparing a presentation itself, on actually like sitting down and writing out the presentation. So the main components of your presentation should be, I'm going to go through them. Actually, I'm going to go through this one by one. So you should start your presentation. This is based on what I see from previous semesters, and people forget to do it. So the first one is that in the title slide, make sure to include the name of the paper, the venue that the paper was published, the author's list, and your name, the venue that you are publishing, or giving the talk, which is the seminar class, and the dates that you are going to give the talk on. This is a good practice for every single talk that you actually do, people to know who you are. Then this should be followed by executive summary, and the goal of the executive summary is to inform the audience what the talk is about from the get-go. So if I'm in a busy conference center, there are many talks going on at the same time and going back and forth to different talks. and I don't have time to sit down and listen to your 20 minutes talk or to get the main idea, give the key idea of your work at first, so the person can understand if they are going to invest the time or not in that talk. And even if they don't want to invest the time, at least it got to know something about your work, the most important points of your work. And this executive summary should follow that classical organization that we follow here: problem, goal, key idea, mechanism, and key results. Then outline. So usually, since we are following a same structure for all of the seminar classes, the outline of the talks are more or less similar. But still, I believe it's quite important to have an outline for your talk, because it gives you as a presenter a much more structured way of going through the presentation flow. Because if you segment the outline and repeat this outline several times, you are informing not only the audience that now I'm going to talk about background, now I'm going to talk about my idea, now I'm going to talk about evaluation. It also gives you some mental guide to know where you are in your presentation. So it is really helpful to manage time, for example. And in terms of execution flow, your presentations will always go from the higher level of abstractions, from the introduction to the background and key ideas, down to the lower level of abstraction, so implementation details. So never start with implementation details from the get-go, because the audience is not warm up the jargons that you're going to use, the concepts that you're going to use, all of those things. So from higher to the lower level of abstraction. This is something, show don't tell, is something that actually you might find in the context of cinema or writing novels. So it's much more preferable to not use exposition. So if it's a movie and I'm describing something, if I put a character to describe something, that's really boring, right? But if I show that scene happening, it's way more engaging. And since presentation is you can think of presentation as also as you would think about cinema, meaning that is a image plus audio type of media, you should use both of them in your favor. So you shouldn't just use audio, because then why I have slides here, I can just tell you the story. You shouldn't just use text, otherwise you can just read. So you should find a way of combining both to support each other. So as an example, so if you look at the paper, there is the description of how the activation procedure works, right? Which I can just write it down here, but it's quite cumbersome, right? A better way of doing that is actually animating step by step of what is written here as is done in the presentation. This takes a lot of time, and I cannot describe precisely how much time this takes, because most of our time is spent on doing these animations and find a way of representing things graphically in a nice way. That takes a lot of time. So don't start the presentation 2 days before you come here to present, because you're not going to have time to do this. It really takes us like really good, like 2 weeks just to come up with good graphics and animate them properly, and several iterations. So think about them as you read, or and also you can reuse. So if there is if you're going to talk about DRAM background, and prior Safari presentations already have good animations for DRAM background, you are fine copying that animation to your slides. Just reference them correctly. Don't copy the entire presentation, otherwise why you are here in the seminar class, right? Prepare the presentation is also some good practice. But if there is something that is something common, like DRAM background, just go ahead and copy the animation. So the second thing is be explicit while drawing takeaways. So if you are presenting an idea or a result or a plot, always help the user getting the idea behind that idea or behind that plot. Because the user does not have time to think while you're listening to you. The audience is getting the ideas and the concepts while you are talking, which might be new, right? And so if there is a takeaway that the user, I don't know why I have it in my mind. The takeaway that the audience needs needs to have, write the takeaway down and tell the takeaway explicitly to the audience, so that the takeaway the message is conveyed precisely. Not final, but also really important is to practice your talk a lot. So what we usually do is to write down a script for your talk. And this script is actually really well detailed. I didn't follow the script over here because it's more chill. But if I'm in a conference venue, I not necessarily try to memorize this script, but I try to have it really, how can I say this? Not necessarily memorized, but is impregnated in me. Like I know exactly what I need to say at every single point in time. And this script is detailed to the click. So if I have a lot of animation, I actually write down, I need to click, I need to click. This is also really good when you're practicing, because if you practice without a script and you start making mistakes, you don't know where to correct them, because you did a mistake now and you might not do the same mistake again, and you might do it again or make a new mistake. So it's really hard to identify those problems. If you have a script and you start by reading that script to yourself and following that script, you can identify easily problems with your animations or problem with your flow in your presentation and all of those things. So it's a really good practice. So finally, styles matter. So how things are organized in the screen is extremely important. So the human eye is really good at identifying patterns on things, and it can get really easily distracted by patterns that are not, things are not following a pattern. So you should always care about and go through slides thinking about, do I have typos? Do I have inconsistencies? Inconsistency here can be, for example, using different fonts in the same slide or in the same sentence. You have a misalignment, or you have a poorly vertical and horizontal alignment in your text. So all of this might sound like nitpicks or something that's not necessarily important, but just looking at this, I don't know you guys, but I look at this, I hate this slide so much just because you see all of those things at once, right? So you cannot pay attention to the blue text, you just pay attention that everything is misorganized or is full of types, right? Your mind just fixate on those things. So beauty is subjective, but this is a graphic view, so you should at least try to follow good practices. So start from a good template. Usually the TH template is not good. It's the font is really small and there is a lot of space for banners and stuff, which are not necessarily useful. So of course, you can always go to a Safari presentation from Onur's webpage, select a presentation that you like and use that as a template. You can create your own template, but try to start from something clean or something that you know that works, so you don't have to reinvent the wheel every single time. So also, if you are not so familiar with what to do, there are many common rules that are good practice. For composition rules for photography, you can also be applied here, like rule of thirds, of the use of empty space to separate things, or repetition to convey idea, or font hierarchy to denote importance of different or cluster things in different ways. Colors is a subject that's really hard to follow, but a good practice is to think about basic color theory. And if you just Google basic color theory, you're going to find the color wheel, and you're going to see how colors go together well. So how there are many different rules of composition, like I forgot the names of them again, but there is the one with the triangle, with the square, all those. So usually when I'm creating slides, I always have the Adobe web page nearby me, and when I pick a color, I follow exactly that rule of composition that Adobe gives to me, because I know that those colors work together. So it's usually a good practice. And this is a personal one, but I think it's really good. Avoid the Calibri font at all costs. The Calibri font, which this one here, is an awful font. And the creator of the Calibri font itself said that it's an awful font, so it was relieved when Microsoft stopped using it. And it's not a beautiful font, and usually they default to Microsoft. So just change it to something else. I don't know. This is Cambria, which I don't like as well. But just pick one that is not Calibri. And that is pretty much what I had. Hopefully those tips are useful. There is something that I couldn't find a place to put over here, but it's really important as well, is to have page numbers in your slides. People often forget to add them. So I don't know if you have a question related to all of those things. Hopefully those tips are useful when you're preparing the presentation. And is there any other question or something? Okay, so thanks so much for your attention.
No, I can use this.
Okay. Hello everyone, my name is Ismail. I'm a first year PhD student at Safer in Zurich. Today I'll be presenting my work, which is recently published in HPC 2024. It's called Functional Complete Boolean Logic in Real DRAM Chips. So Gerald will give a talk about how we can leverage processing using DRAM, which is proposed in prior works by modifying the DRAM circuitry. So in this work, we somehow find a way to perform some of these operations, like AND or NOT, NAND and NOR operations, in real DRAM chips without doing any modification. So I'll be presenting this work, and let's get started. So our motivation is the same. Processing using DRAM can elevate the performance and energy bottlenecks caused by data movements between main memory and processing elements. And prior works show that existing DRAM chips, commercial off-the-shelf DRAM chips, can perform 3-input majority, which again Geraldo talked about, and thus they can perform 2 inputs and an OR operation in real DRAM chips so far. But however, this proof of concept demonstrations cannot perform functionally complete operations such as NAND or NOR, NOT operation, and more than 2 input and an OR operations. So in this study, we tested a total of 236 DDR4 chips from 2 major manufacturers, DRAM manufacturers, and here are key results. We find that off-the-shelf DRAM chips can perform NOT and 2 for 8 and 16 input and NAND or and NOR operations with very high success rate, more than 94%. And data pattern, the data pattern that we operate and the temperature, the DRAM chip temperature, only slightly affect the reliability of these operations, less than 2%. So here's the outline of my talk. I'll start with a brief background, and then I'll state our goal and overview. I'll briefly talk about our experimental methodology, and then I'll show what we did in this work in 3 steps. So let's start with the background. As you may know already, let me recall, here's a pictorial example of DRAM module, which consists of multiple DRAM chips. Inside the DRAM chip, we have multiple DRAM bands, and inside the DRAM band, we have multiple subarrays and sense amplifiers. And inside the subarray, we have 2-dimensional array of DRAM cells, which are connected through word line, and they form as DRAM row, and sense amplifier are connected to these cells through bit lines. And in modern DRAM architecture, we have an architecture called open bitline architecture to achieve high-density DRAM chips. So what that means is these subarrays share the common sense amplifier over there through a bit line. As you can see, like bit line and bit line bar over there. So neighboring subarrays share those bit lines through sense amplifier. During an activation, assume we activate the row from the upper subarray, the lower subarray bit line serves as a reference for the sense amplifier, which is not activated. And this sense amplifier is composed of back-to-back NOT gate. Thus, after a successful activation, if bit line has VDD, let's say the logic 1 value, bit line bar will have the ground, which is logic 0, due to this shared NOT gate. So we will leverage this NOT gate to perform new operations. So for major DRAM operations, we have, as you may again know, activate, which will fetch the DRAM contents into sense amplifier, which enables us to perform read and write operations. And to perform another activate, another read or write operation, we need to perform a pre-charge to prepare the subarray for a new activation. So in this work, our goal is to understand the capability of off-the-shelf DRAM chips beyond just storing data, and rigorously characterize the reliability of this computational capability. And this work, we demonstrate that off-the-shelf DRAM chips can simultaneously activate up to 48 DRAM rows in 2 neighboring subarrays, and can perform NOT operation with up to 32 output operands, and we can perform up to 16 input AND or NOR operations. So here's our DRAM testing infrastructure. We use an infrastructure developed from DRAM vendor, which enables us to perform fine-grained, which enables us to have fine-grained control over DRAM commands, timings, and temperature. As you can see over here, the first one is the connection to host machine, second one is the FPGA board that we use, and third one is the DRAM module that we test with heater pads to control the temperature, and the fourth one is the temperature control, which we can flexibly change the DRAM chip temperature. And this is the DRAM chips that we test in the study. We test a total of, again, 256 DDR4 chips from 2 major manufacturers, SK Hynix and Samsung. And we cover different die revision and chip densities in this work, which is, you can think of a bit different DRAM architecture. And the testing methodology that we conduct in here, we focus on neighboring subarrays, which they share a common sense amplifier. And assume, though they have row A and row B, which are neighboring subarrays, we use activate row A, pre-charge, and activate row B command sequence. Be careful to select the row addresses, row A and row B in this command sequence, and we sweep the timing parameters between each command in this sequence, between act and pre and act. So let's go to the first one. Now we will see how we can activate up to 48 rows in 2 neighboring subarrays. So our key idea, our key observation, is activating 2 rows in quick succession can simultaneously activate multiple rows in neighboring subarrays. So let's see an example here. So in a nominal and in standard DRAM operation, when we issue this command sequence, what happens is at a single time, we will activate only 1 DRAM row. which is either row A at first or row B. However, when we violate this timing greatly, as you can see from 36 nanoseconds to 3 nanoseconds, we observe that we can activate multiple DRAM rows due to the hierarchical row decoder circuitry that DRAM chips have. And to understand this potential and which and how many rows are simultaneously activated, we sweep this row A and row B addresses, where row A in all rows in subarray X, where row B all rows in subarray Y. And here are the key results. We observe that when we conduct this experiment, there are two distinct sets of activation pattern in neighboring subarray activation. First, exactly the same number of rows in each subarray are activated. We observe that we can activate up to 16 rows into neighboring subarrays, a total of 32 rows. And twice as many rows in one subarray are activated compared to its neighbor subarray. So we observe that we can activate 16 rows in one subarray while activating 32 rows in the neighboring subarray, a total of 48 rows. And our key takeaway from this experiment is off-the-shelf DRAM chips can simultaneously activate up to 48 rows in two neighboring subarrays. And there are many, let's say, hypotheses how we do this. Please check our paper for more detail. And let's see how we use this multiple row activation to perform an operation. So here we have a pictorial example where source and destination are in the neighboring subarrays and their cells, and initial source store voltage value of A. And we will leverage this shared NOT gate between those source and destination. I believe you already guessed what will happen, but let me give you the idea. We connect rows in neighboring subarrays through a NOT gate by simultaneously activating them. So we will first activate source, and which will drive its charge from voltage value of A to its bit line, and we activate destination without deactivating the source. What happens is the negated voltage value due to this NOT gate, the destination will store that negated voltage value of A. Let me give you the lower abstraction level voltage. So here, again, we have source and destination. They both store ground value, and bit lines are precharged to VDD over 2. We issue activate source, which will connect source to bit line, and we wait a nominal timing parameter. What happens is it will drive bit line to ground, and then it will drive the negated value to the destination's bit line, which is VDD. And then we will issue back-to-back precharge and activation operation. Activate destination, which is greatly violating the time lower than 3 nanoseconds. So 3 things will happen. It will connect destination to bit line, its bit line, and it will keep the sense amplifier still enabled, which still, let's say, feed those 2 bit lines, ground and VDD, and it will keep the destination bit line still VDD. And when we wait long enough, the negated value of the source, which is the VDD, is written to the destination. And that's why we can perform NOT operation in real DRAM chips, in a theory. So we will characterize this theory, and we have a methodology over there, and we will see the results of the reliability. So again, we sweep row A and row B addresses. Again, those are rows that are in neighboring subarrays, and we will test all rows in those subarrays. And we sweep DRAM chip temperature from 50 degrees Celsius, which is, let's say, nominal operating temperature, to 95 degrees Celsius, which is, let's say, more than the manufacturer recommend, which is more or less is 85 degrees Celsius. And we evaluate the reliability, as I said, and we use a metric to evaluate it, which we call success rate. And we define success rate for a DRAM cell, which we refer as percentage of trials where the correct output of the tested operation is stored in the cell. So, for example, we test a total of 10,000 trials. For example, you see a Ford trial as an example. And for this destination cell, the success rate is 50%, because 2 out of 4 is correct. So we have two main key takeaways. We observe that off-the-shelf DRAM chips can perform NAT operations with up to 32 destination nodes. That means that when we perform NAT operation, we can negate the value and store into 32 DRAM rows at the same time. And the temperature has a small effect on the reliability of this NAT operation. So let me show you the data. Here you see a blank plot. In the x-axis, we have number of destination rows, which means these are the rows that the source's negative value is written to destination rows. And in the y-axis, you see the success rate distribution for every cell. So these are box plots, and in this, let's say, circles, white circles show the mean, and these are each points in the graph. And the main observation that we did from this graph is there is at least one DRAM cell in every number of tested destination rows that can perform the NAT operation with 100% success rate, meaning that in all of the 10,000 trials, we get the correct result. We get the negative value, basically. And our key takeaway, we conclude that off-the-shelf DRAM chips can perform NAT operations with up to 32 destination nodes. And here we evaluate the impact of temperature. We use the destination cells that can perform this operation with more than 90% success rate at 50 degrees Celsius. This is because the experiment takes too much time, and we need to somehow perform pre-filtering, and we select these cells and see the impact of temperature. So here again, we have the same x and y axes, but here we have a hue. The boxes, let me show you. Yeah. Each cluster of boxes shows the temperature, and temperature increases from 50 degrees Celsius to 95 degrees Celsius, from left to right. And here we want to highlight this part, which is the most, let's say, vulnerable part to temperature, as you can see. From 50 degrees Celsius to 95 degrees Celsius, there is only 0.2 variation, like decrease, in every success rate. And we conclude that temperature has a small effect on the reliability of NAT operations. So this was the NAT operation. Now let's see our last experiment performing AND-NAND or AND-NOR in off-the-shelf DRAM chips. So this is a bit tricky, but let me try to be clear as much as possible. So our key idea is to manipulate the bit line voltage to express a wide variety of functions using the multiple row approach. So here is an example. Again, we have two neighboring subarrays. Each subarray have two cells. And the upper subarray we have A and B, and the lower subarray we have, like bottom subarray we have X and Y. And when you perform a pre-charge, it's pre-charged to a predetermined value, which is VDD over 2, which we call it over there is VREF. And when we perform a nominal single row activation, the one of the bit lines will still be the VREF value. So when we perform this multiple row activation, now both bit lines become the function of voltage values that the cells store. For example, the top bit line become the voltage value of A and B, the function of A and B, and the bottom bit line will become the voltage, let's say, function of X and Y. And sense amplifier will try to compare those two bit lines, and if, let's say, the top one is higher, it will drive VDD over there. If low, let's say the bottom one is higher, it will drive VDD over there. And when it's drives VDD to one bit line, the other bit line will become the negative value. So we will try to use this observation or key idea to perform AND-NAND or AND-NOR operation. Let me give you the walkthrough of two input AND and NAND operation using this mechanism. So here we have, again, two subarrays, two neighboring subarrays. First, in the top, we call it reference subarray, ref, and for the bottom one, we call it complete subarray. And here, assume that we store VDD in one cell and VDD over 2 in another cell in the reference subarray. And in the complete subarray, assume we have X and Y. So, and when we perform add, let's assume we open, let's say, all of the 4 cells here. And for the sake of simplicity, before sense amplifier compare this bit line's voltage, the bit lines will have the average value of cell's voltage. So, for example, in the reference subarray, it will become, when we perform this add command, the bit voltage on this reference subarray bit line becomes the average of VDD and VDD over 2, while the complete subarray bit line becomes the average of X and Y. So let's go case by case. So since we have 2 cells, we will have 4 different cases, right? So let's go with the first one where X and Y is 0, which is ground. So their average, since both of them are ground, the average becomes ground, and in the upper subarray, in the reference subarray bit line, the average becomes 3 VDD over 4, which is the average of VDD and VDD over 2. And sense amplifier will try to compare the voltage on the bit line. Since the 3 VDD over 4 is higher than ground, what happens is that the reference subarray cells will have the VDD and the complete subarray cells will have the ground. And this is the result that we have here. And now let's move to the second case. Again, the reference subarray bit line will have 3 VDD over 4, which is still higher than the complete subarray bit line. And then sense amplifier again compares, and the result is the same. And for the third one, as you can imagine, it's the same as the previous one. Again, complete subarray bit line will have VDD over 2, and which is still lower than the reference subarray bit line voltage, and it will have it will store ground in its cells, while reference subarray cells will store VDD. And for the last case, where the things get changed, here now complete subarray bit line has VDD, which is higher than reference subarray bit line. And now the complete subarray bit line, complete subarray cells will store VDD, while the reference subarray cells will store ground. And as you can see here, now the complete subarray, when we perform this operation, complete subarray becomes the AND operation of X and Y. And reference subarray becomes the NAND operation of X and Y. As you can imagine, the NAND operation is because there's a NOT gate over there. If you have AND operation in one subarray, the other subarray will have the NAND operation. So it's because we, let's say, we perform this operation because of we carefully initialize this cells in the reference subarray as VDD and VDD over 2. In the paper, you can find a lot more detail on why we chose this as VDD or VDD over 2, and how we perform OR and NOR operations. As you can imagine, it's very similar. We carefully initialize the reference subarray to find that threshold to realize OR and NOR operations. And you can find more details in the paper. And the characterization methodology is same as before. We sweep row A and row B addresses. And we have 3 key takeaways from these experiments. First one is off-the-shelf DRAM chips can perform 2, 4, 8, and 16 input AND, OR, and NOR operations. And the second key takeaway is they can perform this operation with very high reliability. And the data pattern only slightly affects the reliability of these operations. So let's go to the first one. In the x-axis, we have number of input operands. And the y-axis, again, we have the same reliability metric success rate. Here in the view, we have operation, AND, OR, and NOR. And as you can see, we conclude that off-the-shelf DRAM chips can perform 2, 4, 8, and 16 input AND, OR, and NOR operations. And when we focus on the 16 input operations, AND, OR, and NOR operations have very high success rate, more than 94%. And let's take a look at the impact of data pattern. Here you see the NOR operations in data pattern impact. Data pattern impact on NOR operations. In the view, we have data patterns. We test a total of 2 of them, all logic 1s or 0s in a row, or fully randomly initialized rows. So here, what we observe is that there is only 1.98% variation in average success rate across all number of input operands for NOR operation. And for the other one, the trend is the same. The impact of data pattern is consistent across all tested operations. And we conclude that data pattern slightly affects the reliability of AND, OR, and NOR operations. And you can find the following more in the paper. First, the detailed hypotheses and the key ideas to perform NOT and many input AND, OR, and NOR operations. How the reliability of these bitwise operations are affected by the location of activated rows, the spatial variation, the temperature for AND, OR, and NOR, the DRAM split rate, and the chip density and dilution. And the discussion on the limitation of tested off-the-shelf DRAM chips. The things that we face when we test real hardware. And the paper is available on arXiv, and our source code is also available on GitHub. If you have an FPGA that supports DRAM vendor, you can go and play with the experiments and try to find new things. And let me conclude my talk. So, the experiment demonstrated off-the-shelf DRAM chips can perform functional complete Boolean operations, NAND, NOR, NOT, and up to 16 input AND, NAND, OR, and NOR operations. And we characterize the success rate of these operations on 256 off-the-shelf DDR4 DRAM chips, and we highlight two key results. We can perform NOT and 2, 4, 8, and 16 input AND, OR, and NOR operations with very high success rate, and data pattern and temperature only slightly affect the reliability of these operations. And we conclude that we believe this empirical results demonstrate the promising potential of using DRAM as a computation substrate. If you have any questions, I'll be happy to answer. It's a bit fast, but yes.
Maybe could you repeat? And you had these graphs with the success rate?
Yes.
And why the success rate? Why is it not one number? Why is it a distribution?
So here, for example, right?
Yes.
So it's the distribution because we test the millions of DRAM sets, and we report each value as, let's say, each DRAM cell success rate, and they form a distribution. Yeah.
Yep. For the NOT function, what causes the failure? Is it like a timing thing, or is it
what causes?
Because when it's the cross-coupled inverter, like that, it will almost definitely be the opposite function that we produce. So in what cases will it not be the line bar function that's produced?
So you're saying that in what, let's say, situation that we cannot observe NOT operation?
Yeah, like you mentioned there's a couple of failures that happen in NOT operations. Is it because of the timing, or is it because of something else?
So what we've done here is it's out of specification. So in normal way, you cannot activate more than one node. So we go very out of specification. So as I show you, like act temperature, it's like 36 nanoseconds, and we go down to 3 nanoseconds and 1.5 nanoseconds. And this is not officially supported by the vendors. So we try to do a hack event, and we try to leverage this existing circuitry to show a proof of concept that you can do these things in real DRAM without any modification. So maybe if it's, let's say, officially supported, maybe we can have a higher, maybe like full 100% reliability. But unfortunately, now we don't know yet that answer.
Also, like I think there was a slide that said that 16 of the rows on top could activate either 16 or 32 rows of the neighboring cells. What causes the difference?
Okay. So the row addresses. So it's a very good question, by the way. So we have another paper that tries to reverse engineer the row decoder circuitry in real DRAM chips. So this memory array should be fast, right? It should serve very fast. So to be able to have that let's say fast speed rate, they need to have hierarchical row decoder circuitry. So you can think of as a tree, and when you try to activate one row, you assert multiple signals in that tree. So, but those two rows have some things that are in common, some signals that are in common. So when you activate both of them at the same time, you assert other ones as well. So, and then you can activate 16, 32. And this is probably, so we observe up to 32 in one and 16 for the other. Probably this is also depends on the row decoder circuitry that DRAM chip has. So maybe we have another paper on archive, it's called Pulsar. Over there, it has a pictorial example of how, let's say, hypothetical row decoder circuitry could be done in real DRAM chips. Yeah. Yes.
And so for these operations, when you have multiple, like more than 2 operands, it basically works the same way as the 2 operands which you showed, but you just have to, you connect all the operands on one end of the NOT gate.
Yeah,
and you have to choose the reference voltage on the other end. Like
yes, exactly. So for those operations, our first constraint is we need to activate same amount of rows in 2 neighboring subarrays. For example, if we want to perform 16 input AND operation, we need to activate 16 from reference subarray and 16 from the compute subarray. Okay. It's because of the, so maybe I can give you further information over there. So this is when you sum this reference subarray's cells voltage up, it's 1.5 VDD, right? It's lower than 2 VDD. And so that's why we can, let's say, perform AND. Because if we have 2 VDD, meaning that all of them are 1, we should have the output of 1. That's why we choose the reference subarray as VDD and VDD over 2. For the 16 input, what you need to have is 15.5 VDD in the reference subarray. Because when the compute subarray has all 1s, it will have 16 VDD and it will be higher than 15.5 VDD. That's why it will output as 1. And the other cases, it will lower it. It will be lower than 15.5 VDD and it will result as 0. Maybe that for those detailed examples, maybe you can check the paper for that one.
And yeah, sorry. I think 7 slides further on slide 49, there's this graph. Well, why does it seem that the success rate increases?
It's from 2 to 16,
for example.
Yeah. We also explain it in the paper. So this is because there are corner cases when we have old ones. So sometimes when we have old ones, it's not stable. So here, when you have 2 input operands, you have 4 cases, right? And one of them is old ones. So 1 out of 4. But for 16 is 1 out of 16, which is less, right? So that's why it's the success rate increases, because the occurrence of having all ones, it's less possibility than having all ones in 2 input operation.
Right. Yeah. Thank you.
Yeah.
So if you are performing AND, NAND, or NOR, are you sacrificing like half your memory for compute?
Yes.
The entire bottom neighborings are dedicated for compute.
So can you repeat the question again?
Like, so when you're performing these functions, right, will all your bottom cells all be dedicated for compute because you're comparing it to the top?
Yes. Yes. So again, there should be some system, let's say, design for this purpose, right? It's for efficiency. Maybe you need to have reserved rows over there to perform those things. I'll get to those like say weaknesses. Maybe we can discuss further on that one as well. Any more questions? Okay, thank you. Those are really good questions. Okay, I don't have that fancy stuff that Geraldo has, but let me try. So, the strengths. First, this is the first demonstration of NAND NOR operations and more than 2 input and an NOR operation in real DRAM chips. Total of 256 DDR4 chips are tested. I think it's good. And a rigorous reliability characterization of these operations under various parameters. I didn't show it, but we have the analysis on spatial variation, data pattern, and temperature. And the source code is available online. It can be tested, extended, and be improved. And let's move on to weaknesses. The first one is computation can be done only half of the rows due to the open midline architecture. So let me recall this pictorial example. Here, we can perform on the cells that have the ticks, right? But since the remaining half is connected to the other subarrays, we cannot fully utilize the parallelism that DRAM offers right now, because we need to somehow use them. So in the prior works, they use the same subarray as Geraldo showed you, like measure the tree. They use the whole cells, all cells in the row. But here, since the half of them are connected to the same subarray, and half of them are connected to the let's say bottom neighbor, and half of them are connected to the top neighbor, we can only perform these operation computation only half of the rows, which should be diminished through. And the second weakness is output of the not base operations, not NAND, nor are in the neighboring subarray. So further computation on input and output requires the data relocation. For example, again, we have this pictorial example. Let's assume we want to perform XOR operation. So XOR operation can be represented as A naught and B, or A and B naught, right? So assume you have A and B over there. First, you need to perform that operation to get A naught and B naught. But now A naught and B naught and A and B are in the neighboring subarrays. And there is no inter-subarray row copy operation in real DRAM chips. So we can perform row clone operation that, again, Geraldo showed in this, if they're in the same subarray. But if they're in different subarrays, since there is a NOT gate over there, we cannot, let's say, copy the row as is. So this is another weakness. For example, if you want to do an XOR, you cannot do it natively. And the other weaknesses, like the less important ones, I guess, no evaluation on how applications will benefit from the new in-DRAM operations. This is unclear. And there's no discussion or evaluation on how to integrate these operations into a system. For example, how would you integrate this into SimDRAM's framework? This is not discussed, and this is still, I guess, an open question. And another characterization point that how voltage, like increasing or decreasing voltage, would affect the in-DRAM operations reliability. We don't know. For example, if we decrease the word line voltage, maybe you watch the Dry's talk before, and he showed that when you decrease the VPP, you decrease the RowHammer vulnerability. How will affect this in-DRAM operations reliability? We don't know. So this is another weakness. And only DDR4 chips are regulated. There is no HBM, which is a 3D DRAM and DDR4 chips tested. This is partly because there is no open source DDR5 testing infrastructure and HBM infrastructure yet. So those were my weaknesses. And the discussion was how can we utilize, which is derived from the first weaknesses. How can we utilize all cells in row to perform in-DRAM operations? How can we improve the throughput? So my idea is leveraging the connection between three neighboring subarrays. So let me show it here. So right now we focus on two neighboring subarrays, right? So the red ones are connected to the red bit lines, and the red cells are connected to the top subarray. But the green ones are not connected to anything. So when we perform our AND or NAND NOR operations, we only use the red ones. So assume three consecutive subarrays, and this example, and half of the rows in the middle subarray are connected to the top, which is indicated as red colors, and other half is connected to the bottom subarray. What we can do here, we can divide the data into two parts and store them into top and bottom subarrays. For example, let's assume you have A, B, C. You can store A and B in the top subarray, C and D in the bottom subarray. And then you can have the full throughput, right? It could, again, increase the let's say, latency, because you need to pre-charge that row first, and you need to write it to the bottom subarray, and you need to do perform some tricks to know the in-DRAM mapping, which is not, let's say, as straightforward as just writing whole data into one row. So again, this will need some work. Do you have any opinions or any other things that you can think? Okay, I can move to the second one, and the second one is the drive from the second bit. Is there a way to solve the data relocation problem? So, can we perform the computations on the output of NAND-based operation and input data without this overhead, the data relocation, or with lower overhead? Right now, what we need to do is we need to read it from the DRAM and write it to the same, let's say, in this second neighboring subrange. So one simple solution could be we can store the copy of A and B in the neighboring subarray as well. For example, when we issue the write command from memory controller to DRAM, we can double the write command and say that, yeah, if you're going to write to this row, and write its neighboring subarray as well. So what will happen is it will increase the latency, 2x more write operation, right? So right now, rather than writing to 2 rows, now you're writing to 4 rows. But it will eliminate reading back the output and write it to the other subarrays, where A and B are stored. And again, you purely do the computation inside the DRAM. You're not, let's say, getting those, for example, in the prior works, what you do is you get the result back to CPU, since there is no NOT. You perform the NOT operation on those huge vectors, and you write it back to the. Still, it's cheaper than that, but again, it has some benefits. Yes, do you have any, let's say, idea on like other solutions, or do you see any drawbacks of this solution?
I just wondering, so in this proposal, it would be like every time you do a NOT, you also make this other copy, or just sometimes when you need to?
So again, we need to somehow programmer should give the hint. So right, like I'm gonna use this, let's say this A as an XOR. I need more. I'm gonna let's say perform more computation on this data. Please also write it to the let's say other reserved area. So maybe there should be some kind of hint that programmer should give to the let's say the code, and compiler should know it, and it will send it to the memory controller, and memory controller to the job. Maybe there could be, yeah. But again, since there's a lack of system integration and the design, let's say the wrapper around those computation substrate, I think still there is an open question. Those things. Any other comments or questions? Okay, I guess that's conclude my talk. I hope you enjoyed the talk. That's it. Hope to see your let's say presentations as well. Yeah, thank you very much.